topic here. Yeah. So let us look at some polynomials with complex coefficients. So the set of all such polynomials is a ring. Suppose we have n indeterminates and C is the field of complex numbers. So this is the ring of all multivariate polynomials, so that the coefficients are complex numbers. Okay. This is a shorthand for monomials. A alphas are complex numbers. And we take a set of polynomials, say f1, f2, fs, and we want to understand what are the solutions. So just like linear equations, we can ask the following questions. Let us write this system as star. So does star have a solution? By solution, we mean an n-tuple of complex numbers, such that f1z fsz is 0. So does it have a solution? Just like for linear equations, we ask this question: does a system of linear equation have a solution? So same way we can ask, if I am given a system of polynomial equations with complex coefficients, what are the criteria for existence of a solution? Second, suppose there is a solution. Suppose there is a solution. Then how many solutions are there? In particular, are they finitely many? What is the condition for having finitely many solutions? Or infinitely many solutions? So suppose we have finitely many solutions. If star has finitely many solutions, then how many? So how do we count? Is there a way to predict? Is there a way to predict the number of solutions? So if you had a system of linear equations, then either it has a unique solution or no solution or infinitely many solutions. Yeah. So for linear equation, there are only 3 possibilities: either no solution or one solution or infinitely many solutions. But in case of polynomial equations, that is not the case. You can have any number of solutions. If there is a solution, there can be 100 solutions or million solutions. Yeah. So is there a way to predict the number of solutions? And if I know the number of solutions, then how do we construct solutions? How to construct all solutions? Yeah. So these are some of the questions we can ask about solutions of system of polynomial equations. Yeah. So this subject is studied in a field called algebraic geometry, and we have a name. So look at this set of all solutions to a finite set of polynomial equations. So this is called the variety defined by these polynomials. Or this is also called the set of zeros. Set of zeros of these polynomials. So V is for algebraic variety. So this lives inside Cn. It's a subset of Cn, which consists of common solutions of finitely many polynomial equations. And this is also denoted by Z. Z is for zero, the zero set of F1 up to Fs. Yeah. So now let us see that. So on one hand, I have Cn. This is called affine space, complex affine space. So we are forgetting the vector space structure and simply looking at the points in Cn as n tuples of complex numbers. Now, on the other hand, I have the ring of polynomials. Okay. So in the ring of polynomials, I take a bunch of polynomials, F1 up to Fs, and to this set of polynomials, I am associating the variety defined by these polynomials, which is simply the set of common zeros. Okay, so instead of F1 up to Fs, suppose I take the ideal generated by F1 up to Fs in this ring. So ideal generated by F1 up to Fs, which consists of all polynomials of this type, G1, F1 plus Gs, Fs, where G1, Gs are polynomials with complex coefficients. So take all polynomial combinations of F1 up to Fs. This is clearly an infinite set. Yeah. This is an infinite set of polynomials. This is called the ideal generated by F1 up to Fs. And one notation for this is within the round bracket, we write F1 up to Fs. Okay, that's an important object in this ring. This is the ideal generated by these polynomials. Okay, so this consists of infinitely many polynomials which are obtained by taking linear combinations of F1 up to Fs. So now,
sir, I have a doubt, a small doubt. So, sir, in the zero set of F1, F2, Fs, so we are collecting all the distinct zeros roots.
yes, yes.
Okay.
Yeah.
Thank you, sir.
Yeah, it's a set. It is a set. So a set is supposed to have distinct elements.
Understood, sir. Right.
Yeah, otherwise I would have said multi-set.
Okay.
Okay, it's a set of common solutions.
Thank you, sir.
So now look at the ideal generated by F1 up to Fs. Okay, and this has infinitely many polynomials. If I take a common zero, if Z belongs to the variety defined by F1 up to Fs, okay, then I take a polynomial in the ideal generated by F1 up to Fs and evaluate this at Z, that is also zero. Yeah, because Fi's are zero. Fiz are zero. So this polynomial is also zero. And conversely, if Z is a common zero of of all polynomials in the ideal generated by f1 up to fs, then Z belongs to the variety of f1 up to fs, because the ideal generated by f1 up to fs contains the polynomial f1 up to fs clearly. Yeah, I just take g1 equal to 1 and other gi equal to 0. So ideal generated by f1 up to fs contains f1 up to fs. So if I have a common 0 of all polynomials in the ideal generated by f1 up to fs, it is also in the variety defined by f1 up to fs. So this says that the variety defined by finitely many polynomials is also the variety defined by the ideal generated by f1 up to fs. So I started with a finite system of polynomial equations. Now I have enlarged it to an infinite system of polynomial equations without changing the set of solutions. Okay. So therefore, this says that any algebraic variety is equal to the variety of an ideal, okay, where I is an ideal in this ring R equal to C x1 up to xn. Yeah, so we have R on the algebraic side, and on the geometric side, we have varieties. So you start with an ideal, and to this ideal, associate its variety. Okay. On the other hand, suppose I take a set of zeros. Suppose I take a subset W contained in Cn. Now to this, I want to associate an ideal of W. Ideal of W, which consists of all polynomials which, so that they vanish at every n tuple of complex numbers for all z in W. Yeah. So look at all functions, all polynomial functions which vanish at every point of W. Now this is an ideal. Yeah, you can check if two functions vanish at Z, there's some also vanishes, and if I take such a function and multiply with any other polynomial in R, that will also vanish. So IW is an ideal. IW is an ideal of R. But it has one more property. So for that, I define what is called a radical ideal. Radical of an ideal. So if I have any commutative ring, R is any commutative ring, and I is an ideal, then the radical of I is defined to be all f in R, so that some power belongs to I. Yeah, some power belongs to I. Not just the squares, but some power belongs to I. So all polynomials which are roots of some polynomial in I, they form an ideal. It's called radical of ideal. Exercise, show radical of I is an ideal of R. Yeah. So now let's observe that if I picked a subset of Cn, and to it I associate the ideal of W. So ideal of W, remember, it is all polynomials which vanish at every point in W. Okay, let's show that this ideal of W has the property that its radical is itself. Now, show that radical of I is an ideal of R. Moreover, I is clearly contained in radical of I because I can just take t equal to 1. I can just take t equal to 1. If I take f in I and take t equal to 1, then it shows that I is contained in radical of I. But in general, radical of I can be bigger than the given ideal. And if I equal to radical of I, then we say that it's a radical ideal. It's a radical ideal. Yeah, so ideal of a subset of Cn is a radical ideal. Okay. Yeah, how to show that? So suppose I take an element in the radical. So suppose I have a polynomial in the radical of ideal of W. Then some power belongs to ideal of W. But that says that some power vanishes at every Z in W. But ftz is simply fz to the power t. So a tth power of a complex number is 0 if and only if fz is 0. And that means f belongs to ideal of W. Right? So in this correspondence, from the ring to Cn, I took an ideal and to this ideal I associated an algebraic variety, namely V of I. And from a subset in Cn, I associate an ideal which is consisting of all polynomials which vanish at every point of W. This ideal is a radical ideal. So we don't get all ideals in R. In this reverse process, we only get radical ideals. Okay, we only get radical ideals. So there is an interaction happening between algebra and geometry, and I will prove that in this correspondence, there is from radical ideals. Yes.
How can you sure about that variety will be non-empty?
I am coming to that.
Okay.
Yeah, I'm coming to that. That is the one question. So to say variety is non-empty is to say that given system of polynomial equations is a consistent system, right? So I'm coming to that point. Okay, but what is happening now is that on the algebraic side, I have radical ideals which are their own radicals, and on the geometric side in Cn, I have algebraic varieties, which are varieties of ideals. Now, it's a small exercise for you to prove that variety of ideal is same as variety of its radical. That's not difficult to show. Okay, so we will show that there is a one-to-one correspondence. One-to-one correspondence between radical ideals and algebraic varieties. So these are radical ideals in the polynomial ring in n variables with complex coefficients. Yeah. So this map is take the ideal and map it to the variety. And the reverse map is take an algebraic variety and map it to the ideal of W. Okay. These maps are inverses of each other. This is a one-to-one correspondence. To say it is one-to-one correspondence means if I start with an ideal, construct its algebraic variety, and then construct the ideal, I get back, okay, I will get back radical of I. Okay, so if I is a radical ideal, I get back I, and therefore And the other way is start with a radical ideal, go to its variety, and then go to its ideal. Then I will get back J. Okay, so taking radical ideal to its variety and taking a variety to its ideal, they are inverse operations. This is called strong Null-Stillen-Jats. So I'm going to prove that strong Null-Stillen-Jats. Here we insert strong Hilbert Null-Stillen-Jats. So if I say strong, then there is a weak Null-Stillen-Jats also. Weak Hilbert Null-Stillen-Jats. So weak Hilbert Null-Stillen-Jats, this predicts when there is a solution. When does a system of polynomial equations have a solution, has a solution? This is answered by weak Null-Stillen-Jats. Okay. Yeah. So the weak Null-Stillen-Jats has to do with structure of maximal ideals. So let us first understand the structure of maximal ideals in our ring R in many variables. Okay, so suppose n is 1, then my R is simply a polynomial ring in one variable. Can anybody tell me what are the maximal ideals? In this ring?
Generated by linear polynomials.
Who is talking?
Sakshi.
Yeah, what are the maximal ideals?
Ideals generated by linear polynomials of the form basically xl minus ai.
Yeah, so how does it follow? What theorem implies that maximal ideals in Cx are generated by a linear polynomial? What is the reason for that?
So C is a field.
C is an algebraically closed field, that is the reason.
Yeah.
We can reduce it to linear factors in C.
Right. So this is the fundamental theorem of algebra. Fundamental theorem of algebra says that if I take any polynomial of positive degree, AD xd plus A0, d is bigger than or equal to 1, yeah, then this polynomial has a complex root. F of x has a complex root. We must use this result. So first of all, a maximal ideal in Cx, okay, is a prime ideal. It's a prime ideal and it is not zero. Prime ideals are zero ideal is a prime ideal, but zero ideal is not a maximal ideal in Cx because Cx is a principal ideal domain. This is a principal ideal domain, and there are only two kinds of prime ideal: the zero ideal, and then there are maximal ideals. There are infinitely many maximal ideals. So this fundamental theorem of algebra says that any polynomial has a complex root. But Cx being a principal ideal domain says that any ideal is a principal ideal, but prime ideals which are non-zero, they are generated by irreducible polynomial, but irreducible polynomials are only linear polynomials. Yeah. So therefore, the maximal ideals look like this: some complex number A1, another complex number A2, etc. Yeah. So therefore, if I look at C and take a complex number, then to Z I associate this linear polynomial and take this principal ideal. Call this as the maximal ideal, which is associated to this complex number. This generates a maximal ideal in Cx. Okay, the maximal ideal for Z. And the variety defined by x minus z is simply Z. Okay, this we want to generalize to multivariate situation. So problem. What is the generalization of star to Cx1 xn? Yeah. So earlier in one variable we had C, but now we have Cn, and there are points in Cn: A1, A2, An. Suppose I take a point in Cn. Then on the algebraic side, I have this polynomial ring, and I want to associate a maximal ideal. To this point, I want to associate a maximal ideal. So you can just make a guess from one variable situation. Yeah, look at x1 minus a1, the ideal generated by x1 minus a2, x2 minus a2, and xn minus a. We'll call this ideal as MA, where A is this point. Okay, we need to prove a couple of things. So MA is a maximal ideal. That is an easy fact. Part B, which is called weak null-Schulden-Jahres, says that any maximal ideal of R is of the form MA for a unique point A in C. Is this clear? Any questions so far? Any questions? So the point is, you know a lot about polynomial ring in one variable. You know fundamental theorem of algebra that translates into one-to-one correspondence between complex numbers and maximal ideals in Cx. And it's natural to ask, what is the generalization to multivariate polynomial ring? And this generalization is called weak Hilbert null-Schulden-Jahres. It gives a structure theorem for maximal ideals. Yeah, the maximal ideals in polynomial ring in n variables are exactly the ideal generated by these n linear polynomials: x1 minus a1, x2 minus a2, xn minus an, where a is a given point in Cn. And this is a one-to-one correspondence. A in Cn mapping to the maximal ideal A is a one-to-one correspondence. A single point is an algebraic variety. Single point is an algebraic variety. It is the common set of the set of common zeros of these polynomials, x1 minus a1, x2 minus a2, and xn minus an. Okay. So smallest non-empty algebraic varieties are singletons, but they correspond to largest ideals in the ring. So when you shift from geometry to algebraic side, there is a reversal. Yeah. Smallest non-empty algebraic varieties correspond to largest ideals, proper ideals in polynomial ring. Okay, there are all kinds of ideals in polynomial ring, and all radical ideals, we will prove that they are in one-to-one correspondence with algebraic varieties. So the simplest case of that one-to-one correspondence is the one-to-one correspondence between maximal ideals and points in Cn. So that is the weak nullation Zatz, and I want to prove this fact, okay, today. All right, so proof. Yeah, so for n equal to 1, it is the fundamental theorem of algebra that every maximal ideal corresponds, every maximal ideal in Cx corresponds to a unique point in C. Okay, because every polynomial of positive degree has a complex root. So maximal ideals in Cx are precisely generated by linear polynomials. Yeah. So we want to somehow use this fact for n equal to 1 case and derive the structure of maximal ideals for a multivariate situation. So take a maximal ideal. Suppose M is a maximal ideal of the ring of polynomials with complex coefficients in n variables. So this is a maximal ideal. Okay, I want to show that this maximal ideal is generated by n linear polynomials, x1 minus a1, x2 minus a2, xn minus an. Yeah. So let us go down to polynomial ring in one variable. This is a subring, and I can intersect this maximal ideal to this subring. Okay, let us call this by small m. What can you say about small m? What kind of ideal is this? Can anybody tell me? When I intersect this maximal ideal with polynomial ring Cx1, what kind of ideal do I get? Yeah, anybody? Is it a maximal ideal? Is it a prime ideal? What kind of ideal is this?
Hello, sir. Am I audible?
Yes.
Yeah, yes, sir. So, like, it is, of course, a prime ideal because, it is a contraction of another prime ideal over here.
Yeah.
But like for the maximal case, we use the fact that in Cx1, everything other than 0, every prime ideal other than 0 is a maximal ideal. So it will be maximal.
Yeah, so you are right. There are two possibilities here. M could be 0, which is a prime ideal in Cx1, or M could be maximal ideal. Cx1 is a principal ideal domain. In a principal ideal domain, there are only two kinds of prime ideals, namely the zero ideal and maximal ideal. Yeah. So this M is either 0, the zero ideal, or M will be a maximal ideal. But maximal ideal in Cx1 by fundamental theorem of algebra, they are generated by linear polynomial. So it will be like this. These are the only two possibilities. I want to rule out this possibility. Yeah, this is ruled out. Let us see what will happen. Suppose a maximal ideal in the polynomial ring in n variable intersects to 0. What happens? So look at Cx1. This is included in the polynomial ring in n variables, and then I take the quotient ring. Yeah, M is the maximal ideal of polynomial ring in n variables over a complex field, and I take this quotient ring. Yeah, what can you say about this? What kind of ring is this?
So it is a field.
This is a field because M is a maximal ideal. Yeah, and this is inclusion map. So then I compose these two, these are ring homomorphism. Inclusion map is a ring homomorphism, and pi is the quotient map, that is a ring homomorphism. So kernel of this ring homomorphism is all polynomials in Cx1. Yeah, so that what can you say? What kind of polynomials are in this kernel of pi composed with I?
So things mapping to M.
Yeah, so the residue class of f in R mod M should be 0. That's the image. Image of f is the residue class of f in R mod M, and that should be 0. But this is if and only f belongs to M. So kernel is nothing but M intersected with Cx1. So by the first homomorphism theorem, if I go mod the kernel, then this will be an injective map to R mod M. But I'm assuming M intersected with the Cx1 is 0, right? So this says that polynomial ring in one variable injects into this field. This is a field. Yeah, is this clear to everybody? But you see, this polynomial ring is contained in this field R mod M. So it will contain all rational functions also, because every polynomial is invertible in R mod M. Every polynomial in Cx1 becomes invertible polynomial in Rm. So all rational functions, if I take all rational functions in x1, this is the field of rational functions in one variable. This will be also contained in R mod M. Yeah. So Cx1, the field of rational functions in one variable, injects into this field. Now let's go back to R. R is C x1, x2, xn. This is a vector space. This is a complex vector space. What is the dimension as a complex vector space of R? Yeah, anybody can tell me what is the dimension of R as a complex vector space?
N.
Who is talking?
It is Sir Shayantoni.
Yes.
It is N.
You are saying it is a finite dimensional vector space? Just think of Cx only. In Cx, suppose I take 1, x, x square, x cube. Are they linearly independent? Look at these infinitely many polynomials, 1, x square, x cube, x4, x5. Are they linearly independent?
Yes, sir. Linearly independent.
Yeah. So then in Cx1, x2, xn, if I take all monomials in Cx1, x2, xn, they are linearly independent, right?
Yes.
That's the meaning of indeterminates. X1, X2, Xn, when I say X1 up to Xn are indeterminates, that means there is no polynomial relation among X1 up to Xn. So therefore, all monomials in X1 up to Xn are linearly independent. All monomials in X1, Xn are linearly independent. How many there are? How many monomials are there in X1 up to Xn?
Infinite.
Infinite. Can you be more precise?
Countable.
Countable. Yeah. So the dimension of R as a complex vector space is countable. Okay, this is clear to everybody. Polynomial ring is also a vector space. It is, and the set of monomials is a basis, because every polynomial, every multivariate polynomial is a unique, complex, linear combination of monomials. So monomials are linearly independent. There are countably many monomials in X1 up to Xn. Therefore, dimension of this polynomial ring over the complex field is countable. Yeah, it has countable dimension. It is not finite. It has countable dimension. Okay. When I take quotient of a vector space which is of countable dimension, what can you say about the quotient space? Yeah, suppose I take Cx or x minus 1. Yeah. What is this? Cx says countable dimension, right? And take the ideal. Every ideal is a subspace. By definition, ideals are subspaces. Okay. So I'm taking this quotient space, Cx over this ideal generated by x minus 1. That's a maximal ideal. What is this isomorphic to? This is C. Yeah. Because from Cx to Cx over x minus 1, I just take a polynomial, not this. I just take a polynomial and evaluate it at 1. Then the kernel of this map, if f1 is 0, that means 1 is a root. If 1 is a root, by remainder theorem, x minus 1 divides f. Okay, but kernel is a maximal ideal because the image is the field. Image is a field, so kernel is a maximal ideal. Maximal ideal contains x minus 1, so it must be this. So C is isomorphic to this. This is one-dimensional vector space. One-dimensional C vector space. So this has countable dimension. This also has countable dimension. Just a minute. Yeah. So when I take n variable polynomial ring and go mod ideal, this dimension, let's call this as V, then dimension of V over C is either finite or countable. Yeah. So it can be infinite or it is countable, because when I take quotient, the images of all monomials, they will form a generating set of the quotient space. So therefore, but they may not be linearly independent. So the dimension of V can be finite or it can be at most countable. But it contains Cx1, the field of rational numbers. This is a subfield. And this is also a complex vector space. Okay. So Cx1 is a subspace of a vector space which is either finite dimensional or countable dimension. Okay. Now let me show that dimension of Cx1 over C is uncountable. And that will be a contradiction. It will be a contradiction to the fact that maximal ideal capital M intersects to the zero ideal in C in the polynomial ring in one variable. Okay, and then it will say that the maximal ideal contracts to a maximal ideal in polynomial ring in one variable over C. Okay, so let us show that this is uncountable. This dimension is uncountable. So this is field of rational functions. So let us look at 1 minus. Suppose I look at Cx is the field of rational function in one variable, and look at x1 over x minus z, where z varies over all complex numbers. This is uncountable. This is an uncountable set. Can you tell me why it is uncountable set?
Because C is an uncountable.
Yeah, real field, right? Real numbers are uncountable. C is also uncountable. Okay. Let us show that these functions are linearly independent. 1 over x minus z, this set where z belongs to C is linearly independent. That will be a contradiction. Okay. So suppose there is a linear dependency relation. So let Z1, Z2, Zt be complex numbers, and look at 1 minus, x minus Z1, 1 over x minus Z2, x minus Z2, 1 over x minus Zt. And suppose they are linearly dependent. That means there is a linear dependency relation. There are complex numbers so that this is equal to 0. So there exists B1, Bn as complex numbers so that this relation is true. Yeah, some non-trivial linear combination, suppose, of these rational functions is 0. I want to show that all the BIs are 0. That will show that if I take any finite collection of 1 minus x minus zi, it is linearly independent. Okay. So suppose I have this linear relation, B1 over x minus z1, B2 over x minus z2, Bn over x minus zt, and this sum is 0. I want to show BIs are 0. So what can you do to show BIs are 0? What can you do? I want to show BIs are 0.
B1 z minus x minus z2 into dot dot x minus zt plus B2 x minus z1 into dot dot x minus zt equal to 0. Then put 1 by 1 if first put
Good. I get the idea. So take a common denominator, right? You want to take common denominator. Let us just take 2 of them, and that will give you the idea. Suppose I want to show B1 and B2 equal to 0. You just take common denominator, x minus z1, x minus z2, B1 x minus z2 plus B2 x minus z1, and this is 0. But rational function equal to 0 if and only if the numerator is 0. Now what can you do? after this?
First we put x equals to z1, then we get b1, z1 minus z2 is equal to 0. This implies b1 is equal to 0.
Yeah, because zi's are different.
Prediction of B2.
Yeah. So put x equal to z1 and x equal to z2, you will get b1 and b2 are 0. So that says that these two are linearly independent, and the same trick will work for n rational functions. Just take common denominator, keep on putting x equal to z1, x equal to z2, etc., etc. You will get all the bi's are 0. Okay. So that says that this collection of rational functions is a linearly independent set. It is a linearly independent subset of Cx1. But Cx1 is a subfield of R mod M. And R mod M, we saw that R mod M has countable dimension. This dimension is countable. So exercise. Subspace of a vector space of countable dimension is of countable dimension. That's an easy fact to prove. I'll leave it as an exercise. So we have got a contradiction. So we started with a maximal ideal in polynomial ring in n variables, and then we took polynomial ring in one variable and intersected M with this polynomial ring in one variable, and we showed that this is not 0. And therefore it is generated by a linear polynomial by fundamental theorem of algebra. There is a complex number Z1, so that M intersected with Cx1 is a maximal ideal. Maximal ideal and Cx1 are generated by linear polynomials. So this maximal ideal that we started with contains x1 minus z1. So if I replace this by Cx2, I will get a polynomial x2 minus z2 and so on. So therefore, M contains x1 minus z1, x2 minus z2, and xn minus zn for some complex numbers z1 up to c. So this maximal ideal contains once it contains some polynomial, it will contain the ideal generated by those polynomials, because M is the ideal. So x1 minus z1, x2 minus z2, xn minus zn. Okay. Let us call this as mz, where z is the n tuple, z1 up to zn. And if we show that mz is a maximal ideal, then M will be equal to mz. And we will be done. We will know that structure of maximal ideals in polynomial in n variable, they are given by points in Cn. Okay. Now, why mz is a maximal ideal? Yeah. So mz is the ideal generated by linear polynomials x1 minus z1, x2 minus z2, and xn minus zn. Okay. You want to show it's a maximal ideal. In a ring, how do you show that some ideal is a maximal ideal? Anybody wants to answer? Suppose I'm given a commutative ring and I want to show that some given ideal is a maximal ideal. What are the ways I can do that?
So usually the simplest way is to take a quotient and see if it's a field.
Right. So I want to take a quotient. Okay, I want to take a quotient. So R is x1 up to xn. Okay, but there is slightly different idea. I take a multivariate polynomial and I evaluate this at the n tuple z. Okay. Yeah. So when I substitute in a given multivariate polynomial xi equal to zi, I get a ring homomorphism. Phi is a ring homomorphism. Substitution maps are ring homomorphism. Is phi onto? Is the map phi onto?
Yes, sir.
Yeah, phi is onto, because complex numbers are all at the level of complex numbers. This is identity map. So phi is a surjective ring homomorphism. Okay. So if I go mod the kernel, I get C. So kernel is a maximal ideal. C is a field. Quotient of a ring by an ideal, if it is a field, then it's a maximal ideal. So kernel phi is a maximal ideal. But kernel phi contains x1 minus z1, xn minus zn. So it contains the maximal ideal mz. I mean, mz is contained in kernel phi. But now, do you recall the Taylor's theorem? Suppose I have a multivariate polynomial and fz equal to 0, then when you take Taylor expansion, what is the constant term? If fz is 0, what is the constant term in the Taylor expansion of f around z1, z2, zn?
So it is 0.
Yeah. So take Taylor expansion. Consider Taylor expansion. Taylor expansion of f around z1, z2, zn. So this f will be given by fz plus summation del f over del xi, okay, times xi minus zi, okay, and then quadratic terms, etc. But fz is 0. Okay, so this is contained in the ideal generated by x1 minus a1, because quadratic terms will involve product of xi minus zi. So those are also contained in the maximal ideal generated by x1 minus z1, x2 minus z2, xn minus zn. So kernel is contained in mz, but mz is contained in the kernel. And therefore kernel of phi is mz. So therefore it is a maximal ideal. And therefore our capital M is mz. And we are done. Yeah, so let me recall what we have done. I started with multivariate polynomial ring. I took a maximal ideal, and then I intersect maximal ideal with cx1, then cx2, etc. And in each case, I picked up a linear polynomial. Because all these intersections were maximal ideals of one variable polynomial ring. I picked up these linear polynomials and then look at M, this contains mz, and then finally prove that mz is a maximal ideal, so M must be equal to mz. So this is the weak Nullstellensatz, right? So weak Nullstellensatz. Weak-Nullstellensatz. Yeah, this is a German word. Satz means theorem. Stellen means point, and null means 0. So this is 0-point theorem because it is talking about points. Yeah. So Weak-Nullstellensatz says that there is a one-to-one correspondence. There is one-to-one correspondence between the maximal ideals of R and points in Cn given by Z mapping to Mz. You can check very easily that if Z1 and Z2 are two n tuples and then Mz1 and Mz2 are distinct, distinct points will go to distinct maximal ideals. Okay, distinct points will go to distinct maximal ideals. That's an exercise for you. So the smallest algebraic varieties in Cn are points, and points correspond to largest proper ideals. Okay, largest proper ideals. So that is the Weak-Nullstellensatz. And okay, so any questions? Any questions about what we have done? Okay, let's go back to our aim. When does a system, our one question was, if I am given, if F1 Fs equal to 0 is a system of polynomial equations with complex coefficients, then when does it have a solution? Yeah, can anybody make a guess? Now you know the structure of maximal ideals. So the set of zeros of Fs is also the set of zeros of the ideal generated by F1 up to Fs that we have seen. I equal to F1, F2, take the ideal generated by F1 up to Fs that has infinitely many polynomials. So I can talk about common set of solutions of infinitely many polynomials also. Yeah. So the common set of solutions of finitely many polynomials is the common set of solutions of infinitely many polynomials which belong to the ideal. Okay. So I want to understand when it is non-empty.
Some maximal ideal of C, x1, x2, xn.
Yeah. So what is the condition on I so that there is a solution? Yeah. So let us.
I needs to be proper.
I
should be a proper ideal. It must be contained in a maximal ideal. Okay. So that is the answer. So the zero set is variety of I is non-empty. Okay. It is non-empty if and only if I is not the whole ring. What will go wrong if I is the whole ring? If I is the whole ring, why the zero set of polynomials in I is empty? Yeah, anybody? So I start with a system of polynomial equations, take the ideal generated by those system of polynomials. The set of common solution doesn't change. if I look at the set of common solutions of the polynomials in the ideal generated by F1 up to Fs. Yeah, I have enlarged my system to an infinite system of polynomial equations by going to the ideal generated by F1 up to Fs. Yeah. So suppose that ideal is the entire ring, then I want to say that there are no common solutions. Why that is true?
No, sir.
The constant one.
It's whole ring, so constant polynomial is also
Sir,
there.
Yes. So one,
Yes,
number one or non-zero constant belongs to ideal, right? But non-zero constant don't vanish at any point. Variety of I is same as the variety of F1 up to Fs. So if there was a common solution of F1 up to Fs, it is also a common solution of the constant polynomials in I. If I equal to R, it has lots of constant polynomials, and constant polynomials have no common solutions. So if I equal to R, then it is an inconsistent system. What we want to show is the converse. That is the only way inconsistent system will arise. That is, if F1 up to Fs generate a proper ideal, there will be a common solution. So if I is a proper ideal, if I is not equal to R, then we know that I is contained in a maximal ideal. Maximal ideal are of this type mz. So all polynomials, each polynomial fi belong to mz. But mz is generated by x1 minus z1 and xn minus zn. So my polynomial is a polynomial combination of x1 minus z1, then gin xn minus zn, and this says that fi z1 z2 Zn is 0 for all I, and therefore Z belongs to the variety of F1, F2, Fs. So this is the consistency criterion. If a system of polynomial equation has a solution if and only if the ideal generated by F1 to Fs is the whole ring, which means that so system is inconsistent. System of polynomial equation is inconsistent. If and only if one can be expressed as a polynomial combination of these given polynomials Fs for sum G1 to Gs. So you might ask, no, how do I show that one cannot be a polynomial combination? Am I going to test that given no matter what GIs are, I can never get 1 equal to G1, F1, Gs, Fs? Yeah, so there are algorithms to determine whether a given system of polynomials is the whole ideal, generates the whole ideal. That is an algorithm. There is an algorithm to test whether a given system of polynomials, the ideal generated by a given system of polynomials contains 1. So this is an algorithmic process. It doesn't require you to do any numerical computation. It is a completely symbolic process. Okay. So by using that algorithm, we can determine whether a system of polynomial equations has a solution or not. Simply go to the ideal, use that algorithm to test whether it is a unit ideal, whether it gives rise to the whole ring. Okay. So this is the consistency criterion. Okay. So consistency criterion, whether a system of polynomial equations has a solution or not, we deduce this criterion using the weak null-Shanjats. The weak null-Shanjats is giving us the structure of maximal ideals. That maximal ideals are in one-to-one correspondence. That is, in the polynomial ring over the complex field, the maximal ideals are one-to-one correspondence with points in Cn. Okay, so that is the weak Null-Shinjats. I want to now go to the strong Null-Shinjats. If you first, so are there any questions? Are there any questions so far what we have done? So there are natural questions about system of polynomial equations. And one natural question we have already tackled, that when is the system consistent? Okay. Now we want to move to the other questions. When can you say there are finitely many solutions? And if there are finitely many solutions, how do we determine an upper bound? How can we calculate an upper bound on number of solutions? Because before you can list the solutions or construct the solution, you should know how many there are. Yeah, just like polynomial in one variable, the degree tells you how many solutions can be there. Yeah, so by some method like Newton's method, if you try to construct the roots, one should know the degree of the polynomial, and the degree of the polynomial gives an upper bound on number of solutions. So that one variable result, that the degree gives an upper bound on number of solutions, we want to now find an analog of that result for multivariate polynomial equations. That if there are finitely many solutions, then can we a priori find an upper bound on number of solutions? Okay, so for that we need this stronger version of Null-Shinjats. The weak version allowed us to give a consistency criterion. The strong version of Null-Shinjats will allow us to actually give an upper bound on number of solutions. Okay, so what is strong Null-Shinjats? So as I pointed out, we have two sides. One is the geometric side. So I have this Cn is the affine, this is called affine space of dimension n. Inside Cn, I have algebraic varieties, various kinds of algebraic varieties. So if I is the whole ring, I get empty set. So empty set is an algebraic variety. If I is a maximal ideal, then the variety of I is a single point. So single points, points in Cn, they are also algebraic varieties. Any finite set of points in Cn is an algebraic variety. I think that can be an exercise for tutorial. So in Cn, there are all kinds of algebraic varieties. Is there a question? Anybody has a question? Yeah. So on the algebra side, I am working in polynomial ring over complex field in n variables. Okay, and I'm taking so the maximal ideals. I know the structure of maximal ideal. They correspond to points in Cn, and I want to now go to other kinds of ideals. So these are radical ideals. I want to show that there is a one-to-one correspondence between radical ideals and algebraic varieties. Given by, take an ideal I and go to its variety, and the reverse map is given by, take an algebraic variety and look at ideal of W. So ideal of W, remember, it is all polynomials which vanish at every point of W. Okay, you can show that this is a radical ideal. It is its own radical. So you want to establish a one-to-one correspondence between radical ideals and algebraic varieties. So we want to show that these two maps are inverses of each other. So we want to show that these two maps, that is taking a radical ideal and going to its variety, and taking a variety and go to its ideal, these maps are inverses of each other. So these are inverses, which are means this is equivalent to establishing these two facts, that that the ideal of variety of an ideal is its own radical, where I is any ideal of the polynomial ring. This is one. Second, you take ideal of a variety and then take its variety. It is equal to W itself. This is left as an exercise. This is an easy thing to prove. And this is called strong Nullstellensatz. This is the statement of strong Nullstellensatz. Okay. Yeah. Now I mentioned earlier that if I take ideal of any subset, if W is any subset of Cn, then its ideal is a radical ideal. Now, I is always contained in ideal of variety of I. Yeah. Ideal of variety of I consists of polynomials which vanish at all common roots of all polynomials in I, and certainly I is contained in this. This is clear. But this is a radical ideal. So it is its own radical, but if I have an ideal I contained in J, then radical of I is certainly contained in radical of J, and therefore radical of I is contained in ideal of variety of I. Okay. So I want to prove this side now. Okay. Yeah. So I want to take a polynomial in ideal of variety of I and show that it is contained in the radical of I, which means some power of it is there. So I will prove the contrapositive. Okay. So suppose I take a polynomial which is not in the ideal of variety of I. Let G be not in the ideal of variety of I. Then I will show that G is not in I, radical of I. Okay. So if I have a polynomial which is not in the ideal of variety of I, then that means, okay, then we will arrive at a contradiction. Okay. So this is slightly non-trivial proof. So this is the non-trivial step. Let T be a new variable. So our original ring was polynomial ring in n variables. Now we go to polynomial ring in one variable over R. So I have now n plus 1 polynomial ring in n plus 1 variables. Okay. So inside this polynomial ring, let us look at, so F1, Fm or Fs, these were the original polynomials, F1 up to Fs, we generated my ideal. And now G is not vanishing. It is not in the ideal of variety of I. So ideal of variety of I consists of polynomials which vanish at every point in variety of I. And G is not in this. Okay. So look at Tg minus 1. Take the ideal generated by the original Fi's. So I is generated by these polynomials, F1 up to Fs. And now form a new polynomial Tg minus 1. So Fi's don't contain any T. G doesn't contain any T. But I have this Tg minus 1. That is a polynomial in RT. I can consider this ideal generated by this S plus 1 polynomials. Okay. Yeah. Right. So I want to show that this is not a proper ideal. It is equal to this. This is my claim. that this is the whole ring. Okay, so suppose it is not the whole ring. Then by weak Null-Shenjats, these S+1 polynomials will have a common solution. So if this ideal is not the whole ring, then by weak Null-Shenjats, there is a common solution. There exists a common solution. B1 up to Bn and Bn plus 1 belong to the variety of this ideal. Yeah. This says that F1, B1, Bn, Fs, B1, Bn, they are 0 because Fi's don't involve xn plus 1. I mean, they don't involve t. So Fi's are vanishing at this B1 up to Bn only. Okay. And G, yeah, if G belongs to the ideal of variety of I, then G vanishes at B1, Bn, Bn plus 1. Yeah, but if I look at Tg minus 1 and substitute B1 up to Bn plus 1, what do I get? What do I get? Minus 1, right? Because G is vanishing. G is vanishing. If G is an ideal of V, variety of I, G is vanishing. So this is minus 1, but that is a contradiction. So therefore, this set of polynomials, F1, Fs, and Tg minus 1 have no common solution. So by weak Null-Shenjats, they generate the whole ring. So therefore, 1 can be written as G1 F1 plus GS Fs plus GS plus 1 Tg minus 1, where Gi is Gs plus 1, they are polynomials in the bigger polynomial ring. So I have this polynomial identity involving x1 up to xn and t. There are now s plus 1 variables, and this is a polynomial identity. So in a polynomial identity, in this polynomial identity, which is happening in the polynomial ring in n plus 1 variables, I can then substitute this t. Okay, I can substitute t equal to 1 over g. G is not 0. I can substitute 1 over g, and the identity will still be valid. So that means 1 equal to g1 x1 up to xn, and there can be a t in that. So I put t equal to 1 over g. F1. F1 doesn't have a t in it, so F1 remains the same. Plus g2 x1 xn 1 over g. F2. And so on, plus gs x1 xn 1 over g fs. Okay, so some power of g will be there in all these expressions in the denominator. So clear the denominator, clear powers of g in denominator everywhere. That means I will multiply by g to the r on both the sides, where r is the maximum power of g, which occurs on the right hand side in denominator. Then I clear the denominator and I get gr equal to g1 x1 up to xn, and then this 1 over g will go away and some polynomial will occur, but I will get this f1. F1 is not changing, right? When I put t equal to 1 over g, f1 is not changing. So I get some h1, hs, fs. That's it. So this is in the ideal generated by f1 up to fs. So some power of g is here. So g belongs to radical of I. Okay, so therefore, radical of I is the ideal of variety of I. This is the strong Null-Schansatz, and next time I will show how the strong Null-Schansatz enables us to find an upper bound on set of common solutions of a system of polynomial equations which has only finitely many solutions. So you can say this is the generalization of fundamental theorem of algebra. I will show the application next time. So fundamental theorem of algebra says that degree of the polynomial is an upper bound on number of roots of the polynomial. Yeah, sometimes there are roots which have multiplicities that can happen even in dealing with system of polynomial equations in many variables. But we will give an upper bound on number of common solutions of a system of polynomial equations in n variables, which will be derived by using the strong Null-Schansatz. Okay. So in this first lecture, we have learned weak Null-Schansatz and strong Null-Schansatz. These are starting points of very basic algebraic geometry. And next time I will show how these two results, weak and strong Null-Schansatz, can predict the number of common roots of a given system of polynomial equations. Okay. And then we will use this also to actually construct the solutions using eigenvalues of matrices. There also I will take help of strong Null-Schansatz. Okay, so I think our time is over and we will stop here.